Now let's consider the cross product, that is the curl. The curl is written as del cross V and is also represented just like the cross product operator in the determinant form: x cap, y cap, z cap, del del x, del del y, del del z, vx, vy, vz. This is the determinant form, which is given as, if we work out the determinant, we will find x cap del vz del y minus del vy del z plus y cap del vx del z minus del vz del x plus z cap del vy del x minus del vx del y. This is the form of curl. And now let's consider the geometric interpretation of curl. That's quite interesting. Curl means the whirlpool of a vector. What do we mean by that? Let's consider a few examples and try to clarify this. Let's first draw a picture of a Cartesian coordinate system and a vector field in this system. So this is the x direction, this is y, and this is z. As we mentioned, curl is a whirlpool of a vector. If we have a vector field that points along the arrows that I am drawing now, we can clearly see that it will have a curl. Let's work this example out. If we have this kind of a vector field, the vector field can be represented as minus y x cap plus x y cap. Now if we work out the curl for this vector field, this can be given as the determinant x cap, y cap, z cap, del del x, del del y, del del z, minus y is the x component of it, x is the y component of the vector, and the z component is 0. So this determinant. And if we work out the determinant, it turns out to be x cap del del y of 0 minus del del z of x plus y cap del del z of minus y minus del del x of 0 plus z cap del del x of x minus del del y of minus y. Now if we work it out, we will see that this quantity goes to 0. Here we are taking a partial derivative of x with respect to z, so this will go to 0 clearly. Here we are taking a partial derivative of y with respect to z, this will go to 0. Here we are taking derivative of a constant, this goes to 0. This quantity sustains and becomes 1 because it is a partial derivative of x with respect to x. This becomes minus 1 and in front of that there is a minus sign, so plus 1. and as a result the curl becomes 2z cap at everywhere in the Cartesian space. That's what we find in this case. Okay, let's consider another vector field where we will have again a Cartesian coordinate system. This is x direction, this is y direction, and this is z direction, and this time the vector field looks like this. And when we reverse x, this changes sign. When we go to negative x, this thing changes sign. Something like this. This vector field can be described with the expression vector v is given as x y cap, because y cap is the direction of the vector field, and when x value is positive it points along y cap, when the value of x is negative it points opposite to y cap. Now let's try to evaluate the curl of this vector. So curl of v in its determinant form can be written, it's very simple. And although the whirlpool of the vector field is not clear from this picture at all, if you work this determinant out, you will get the curl to be z cap. So this vector field does have a non-zero curl, and that means the vector field has a finite whirlpool, that is of z cap amount, at every point of it. That's something interesting to see, and this is how we can also understand the geometric meaning of curl. That's very important. Now let's consider few product rules in case of vector calculus, vector differential calculus. In case of ordinary derivatives, if we don't have any vector involved, then there are few rules of addition of please remove this later. When we consider ordinary derivatives, then we have few rules for the derivatives, that is, if we have d dx of f plus g, two functions, that becomes df dx plus dg dx. We have also product rule d dx of a constant multiplied by the function of x. This is the constant comes out, and then df dx, we are all aware of it, and if we take the derivative of the product of two vectors, that is fx times gx, we get f dg dx plus g df dx. And if we have the quotient, then the quotient rule comes, that is, if we have the vector f divided by the function of x, that is fx, divided by the function of x, that is gx. If we have this kind of a situation, we get g df dx minus f dg dx divided by g squared, that is the numerator, the denominator squared. So there are similar rules for vector differential calculus. The gradient of the sum of two scalar fields, this is given as the sum of the gradients of the scalar fields. This. The divergence of the sum of two vectors is given as the sum of the divergence of the two vectors. And the same thing holds for curl as well. The curl of the sum of two vectors can be given as curl of A plus curl of B. Now comes the product rules. If we take the gradient of a constant multiplied by a scalar field, that is given as the constant comes out multiplied by the gradient of the scalar field. And the same thing holds for divergence. So, the divergence of a constant multiplied by a vector is given as constant multiplied by the divergence of that vector. Same thing holds for curl as well. Obviously, curl of k times a vector is given as k times curl of a vector. Now, if we have the product that leads to a scalar, that means product of two scalar fields, or the scalar product of two vector fields, there are certain rules for this for vector differentiation, and there are other kind of products that lead to vectors. That means there is a scalar field multiplied by a vector field, or the cross product between two vector fields. There are different product rules for that. For the first case, we have the gradient of the product of two scalar fields. That's given as f gradient of g plus g gradient of f, just like what we have seen in case of scalar differential calculus. And the gradient of the dot product of two vectors, this is given as A cross the curl of B plus B cross the curl of A plus A dot del B plus B dot del A. In this context, it is important to understand what is these things like A dot del. So, if A is written as Ax x cap plus Ay y cap plus Az z cap, and del is given as x cap del x plus y cap del y plus z cap del z, then this operation gives us an operator itself, a scalar operator, that is ax del x plus ay del y plus az del z. This is an operator and we cannot really commute this dot product in the other way around. That means we cannot really bring this del operator to the left and take the a vector to the right. That is not allowed. So we end up with a scalar differential operator as a result of this dot product. Okay, then there are similar cases for divergence, similar rules for divergence. Divergence of a vector field multiplied with a scalar field, that's given as f divergence of A plus A dot the gradient of this scalar field, and as a result of this we get a scalar quantity out of this divergence. The other rule for divergence is the divergence of A cross B, that is given as B dot curl of A minus A dot curl of B, and the expressions for the curls can be given as curl of FA is if curl of A minus A cross gradient of F. And the curl of a cross product is given this way, curl of A cross B. This quantity is B dot del A minus A dot del B plus A del dot B minus B del dot A. Now, if we go for the second order derivatives, then we will get the following rules. The divergence of the gradient of a scalar, we can calculate this one and we will find that this quantity becomes x cap del x plus y cap del y plus z cap del z dotted with del t del x x cap plus del t del y y cap plus del t del z z cap, and this will be del 2t del x2 plus del 2t del y2 plus del 2t del z2. As expected, the divergence gives us a scalar, and this is in a shorthand notation written as del square of t. This del square operator is also known as the Laplacian. Remember, del square is a scalar operator, and hence we didn't put any arrow on top of it. Now we can consider the curl of a gradient. So, this quantity can be expressed in the determinant form as x cap, y cap, z cap, del x, del y, del z, and del t del x, del t del y, del t del z, the determinant of this, which is, if you work out carefully, you will find it must be 0. That implies that the curl of the gradient of a scalar is always 0, and this result is very important. We will make use of this result in defining scalar potential for conservative force fields. Okay. Then let's consider the other kind of operation, the gradient of a divergence. If we consider the gradient of a divergence, that means the gradient of the divergence of vector v, this quantity can be evaluated as this will be del square of the vector, which is nothing but del dot del of the vector v. There can be other kind of operations, that is divergence of a curl. This is expressed as the divergence operator acting on the curl of v, and we can also show that this quantity goes to 0, and this is also very important because we can make use of this result to define vector potential. And then comes the curl of a vector. That's written as curl of v, and we can show that this can be written as the gradient of divergence of v minus the Laplacian operator acting on the vector v. So these are the expressions that we need for vector differential calculus, and we will do some examples related to the vector differential calculus.